Okay, we continue with Koenig's theorem. By induction on delta H, this yields a proper delta H coloring. Show that for every bipartite graph G with maximum degree K, there is a K-regular bipartite graph H containing G. Add vertices to smaller partite of G, then add edges to vertices with degree smaller than K until becoming K-regular. If we become K-regular, we also said for every K-regular bipartite graph has a perfect matching, then this proves the chi prime equal delta. One factorization. For a regular graph G, proper H coloring with K equals chi prime equals delta colors is equivalent to decomposition into one factors. This is perfect matching. One factorization, a decomposition of regular graphs G into one factors, is a one factorization of G. Example: an odd cycle is not one factorable. Chi prime greater or equal to delta. And Petersen graph. The Petersen graph is 4-edge chromatic and 3 regular, 3-edge colorability requires a one factorization. Deleting a perfect matching leaves 2 factors here. The one factorization could be completed if these cycles were even. So we consider the cases by the number of cross edges used, which is denoted by M. Here we use M equals 0, M equal 2, M equal 4, because every cycle uses an even number of cross edges. Then C5 is 3 colorable, so the graph is 4 colorable. Weising-Gupta's theorem. We consider simple graphs and make delta G plus 1 colors available for proper H coloring. Theorem: if G is a simple graph, then chi prime smaller or equal to delta plus 1. Here chi prime is 6, delta x 6. Here chi prime is 3, delta is 2. Every edge has two, every vertex has 2 connections, so maximum of these are also 2, but chi prime is 3 because we cannot color the, for example here, green, blue. We cannot either green or blue here, so we should give red here, so chi prime is 3. Proof: let F be a proper delta G plus 1 H coloring of a graph G prime of graph G. If G prime isn't equal to G, then some edge of UV of G is not covered by F. Extend coloring to include UV edge. Call this E of G augmentation. After coloring all edges of G minus G prime, we obtain proper delta plus 1 edge coloring of G. We continue the proof. We try to augment coloring using edges of G minus G prime. So, since the number of colors exceeds delta of G, every vertex has some color not appearing on its incident edges. Let A0 be a color missing at U. We generate a list of neighbors of U and corresponding list of colors. This is the first step of augmentation. Then we downshift from I. Let L be the smallest index such that a color missing at VL is in the list of A1 to AL. Let this color be AK. Instead of extending the list, we use this repetition to perform the augmentation in one of several ways. The color AK missing at VL is also missing at VK-1 and appears on UVK-1. If A0 does not appear at VL, then we downshift from VL and use color A0 and UVL to complete the augmentation. Hence, we may assume that A0 appears at VL. So we continue to the proof. Let P be the maximum alternating path of edges colored A0 and AK that begins at VL along color A0. There is only one such path because each vertex has at most one incident edge in each color. We ignore edges not yet colored. To complete the augmentation, we will interchange colors A0 and AK on P and downshift from an appropriate neighbor of U depending on where P goes. Okay, if P reaches VK here, then it arrives at VK along an edge with color A0, follows VKU in color CK, and stops at U, which lacks color A0. In this case, we downshift from VK and switch colors on P. Here. If P reaches VK-1, then it reaches VK-1 on color A0 and stops there. Because AK does not appear at VK-1, in this case, we downshift from VK-1, give color A0 to UVK-1 and switch colors on P. If P doesn't reach VK or VK-1 here, then it ends at one vertex outside of this set. In this case, we downshift from VL, give color A0 to UV1, and switch colors on P, rightmost one. So in each case, the changes described yield a proper delta plus 1 edge coloring of G prime plus UV. So we have completed the desired augmentation. Okay, graph class. For simple graphs, we have only two possibilities of chi prime. Graph G is class 1 if chi prime is delta, equal to delta. Graph G is class 2 if chi prime equals to delta plus 1. Determining whether a graph is class 1 or class 2 is generally hard, and we seek conditions that forbid or guarantee delta H colorability. Examples of such conditions are in the exercises of 24 and 27 in the Book of West. As a remark, there is an obvious necessary condition for graph to be class 1 that is conjectured to be sufficient when delta is bigger than 2/10 of number of vertices of G. the 3/10 of number of vertices of G. A subgraph of G with odd order is an obstruction to delta H colorability if it has too many edges. Over full subgraph means a subgraph of H of a simple graph G is an overfull subgraph if n of H is odd and 2 E of H over n of H minus 1 is bigger than delta G. Overfull subgraph properties are they are of odd order. Overfull graphs are class 2, that is, they require at least delta plus 1 colors in any edge coloring. Overfull subgraph S of a graph G requires delta of G equals delta of S. Overfull conjecture. A graph G with delta G bigger than n over 3 is class 2 if and only if it has an overfull subgraph subgraph S such that delta of G is equal to delta of S. The Peterson graph with a vertex deleted shows that condition is not sufficient when delta is equal to number of vertices of G over 3. The overfull conjecture implies the one factorization conjecture. If R is more than M or M minus 1 if M is even, then every R regular simple graph of order 2m is class 1. Okay, now Shannon's theorem. Shannon's theorem, if G is a multigraph with no loops, then chi prime is smaller or equal to 3 over 2 times delta of G. Proof is K is equal to chi prime. We assume K is bigger or equal to 3 over 2 times delta of G. Let G prime be a minimal subgraph of G with chi prime of G prime is equal to K. Since K is smaller than delta G prime and M G prime, this is Weising-Gupta for multigraphs, and also delta of G is equal to delta of G prime. We obtain delta of G over 2 smaller or equal to mu G prime. Mu G was maximum of the multiplicities of all vertex pairs x, y, and G. Let E with endpoints x, y be an edge with multiplicity mu G prime. Let F be a proper K minus 1 edge coloring of G prime minus E. In G prime minus E, both x and y have degree at most delta G minus 1. So under F, at least K minus 1 minus delta G minus 1 colors are missing at X, and similarly at Y. No color is missing at both, since G prime is not K minus 1 edge colorable. Accounting for these mu G prime minus 1 colors used on the edges with endpoints x, y, and x, y yields here a long equation becomes K smaller or equal 3 over 2 delta of G. Okay, now we come back to characterization of line graphs. Characterization of line graphs can lead to good algorithms to test whether a graph G is a line graph, and if so, to obtain H such that L of H is equal to G. For example, to illustrate the ideas, we prove that rightmost graph below is not the line graph of a simple graph. Here, the kite G, two triangles with a common H, is the line graph of the pole H. Here, a claw plus an edge. By case analysis, we find that H is the only simple graph whose line graph is G, and the edges becoming the vertices of degree 2 in G must be dashed edges. The rightmost graph adds a vertex to G here, having only the vertices of a degree 2 as neighbors. The result is not a line graph, because there is no way to add an edge to H that shares an endpoint with each dashed edge without sharing an endpoint with a solid edge. Here, cross theorem. For a simple graph G, there is a solution L of H G is equal to G if and only if G decomposes into complete subgraph with each graph of G appearing in at most 2 in the list. Our first characterization encodes the process of taking line graphs L of G. The proof: for necessity, if G is L of G and H is if G is L of H and H is simple, then each vertex of H with degree more than 2 generates a clique, and this clique corresponding to edges incident to V. These cliques partition edges of G. Furthermore, each vertex of G belongs only to the cliques generated by the 2 endpoints of E, which are endpoint of H. For example, when G is a kite, we can partition E of G into three cliques: a triangle plus 2 edges, each vertex covered at most twice. These 3 cliques correspond to vertices of degree at least 2 in the pole. The rightmost graph below does not have such a partition here. For sufficiency, let S1 to Sk be the vertex sets of specified complete subgraphs. We construct H such that G is equal to L of H. Isolated vertices of G become isolated edges of edges of H. So we may assume that small delta of G is more than 1. Small delta of G means the smallest number of connections of vertices. Let V1 to Vn be the vertices of G that appear in exactly one of S1 to Sk. Give H1 vertex for each set in a list A equal to S1 to Sk and V1 to Vl, and let vertices of H be adjacent if the corresponding set intersect. Each vertex of G appears in exactly 2 sets in A and no two vertices appear in the same two sets. Hence, H is a simple graph with one edge for each vertex of G. If vertices are adjacent in G, then they appear together in some SI, and the corresponding edges of H share the vertex of S. Hence, G is equal to LH. Van Roy and Mills theorem. Weave's theorem. Krauss characterization does not directly yield an efficient test for line graphs because there are too many possible decompositions to test. This theorem of characterization of linear graphs tests substructures of fixed size and therefore yields a good algorithm. We say that each triangle T is odd or even as defined below. T is odd if n of v intersection with v of t is odd for some vertices of G, and the same thing for even but for every vertices of G. An induced kite is a double triangle. It consists of two triangles sharing an edge, and the two vertices not in that edge are non-adjacent. Theorem. Now we come to Van Roy and Weave's theorem. For a simple graph G, there is a solution to L of H equal to G if and only if G is claw-free and no double triangle of G has two odd triangles. Okay, the proof is, for the necessity, we suppose that first we suppose that G is equal to L of H. So this should be claw-free. A vertex E in G with neighbors x, y, z corresponds to an edge E in H incident to edges x, y, z. Since E has only two endpoints in H, two of x, y, z are incident at one of them, and hence are adjacent in G. This forbids the claw as an induced subgraph of G. And no double triangle of G has two odd vertices. For the necessity, the vertices of double triangle in G must correspond to the edges of a pole in H. In particular, the vertices of one of these triangles in G correspond to the edges of triangle in H. This triangle must be even because every edge in H incident to the exactly one vertex of a triangle shares an endpoint with exactly two of its edges.